Good morning. It's really good to, I know it's been a lot of days since we've seen each other. I just got to tell you a little bit about yesterday. Uh, I don't like to do this, but I got in at 12:30 a.m. at my house, and my driveway had 18-inch snowdrift in it. And I thought, well, I'm going to try to plow ahead and get into my garage. And I didn't. I got stuck in my driveway. The snow, underneath the car was just filled up. And so, anyway, long story short, I was still unburying Friday morning. So that's why I gave you that video to do. Okay, so my question, let's start off with any questions you might have concerning the video of 2.2 last time. We were doing an introduction to limits, and we were trying to get used to this idea that we can look at the numbers and how they approach something, and then we can also kind of see it graphically. Does anybody have, on the assignment or on the material, do you have any questions? '31. All right. Number 31. Let's take a look here. Oh, I don't think you had 31, did you? I've got that crossed out. Why did I cross that out? Let's take a look at the book here. Okay, number 31. Oh, yeah. So did I have that in the assignment? I should not have, because I didn't really talk about, I'm sorry, but that wasn't included in my lesson, so I may have goofed. So anyway, I apologize. That shouldn't have been on there. My fault. And notice I made the mistake too here. As I'm looking at the assignment, do you see what I did? I started doing number 31 and then I crossed it out. So I don't know. I'm sorry I didn't communicate that properly. Anyone else want to talk a little bit about 2.2? Well, our new lesson is 2.3, evaluating limits instead of what? Intuitively, like we did last time, by looking at what the numbers approached or looking at the graph. Today, we're going to learn an algebraic technique, we're going to learn how to evaluate limits analytically. That's the big difference here. So first we have some what the book calls basic limits. And the very first one is the limit of b as x approaches c is b. So in this case, this limit doesn't have anything to do with x. And so, it's like saying the limit of 3 as x approaches 20 is 3. So in other words, x has nothing to do with the problem. So that's kind of a weird one, but that's what it amounts to. It's like, yeah. So anyway, and number 2 says, what's the limit of x as x approaches c? Well, as x approaches c, it's going to be c. And so these are so obvious, sometimes it's a little hard to see them. And number 3, the limit of x to the n as x approaches c. And as x approaches c, just replace the x with a c, and c to the n. So those are easy and kind of incredibly obvious, but we had to get those out of the way. All right. Now, I have really good news for you. Limits work just the way you'd like them to. Let me explain. So, on the top, we have the given. The given is, as the function f of x, what happens to the limit of that as x approaches c? Let's say the answer is some number L. And the limit as g of x approaches, as x approaches c, is k. Well, with that in mind, just what you'd expect would happen. What's the limit as x approaches c as of b times f of x? Well, if it, without the b being multiplied, it was L, guess what? The limit is b times L, just what you would expect. So in other words, if you multiply a function by a number, that's exactly what you do with the limit. The limit gets multiplied by that number. And then the next one, just what you'd think. If you have two functions being added, what do you think is the limit? The sum of the individual limits. So all of this, I mean, there's absolutely no surprise here at all. One caution, and number 4, what happens when you want to take the limit of a quotient? Function f divided by function g. Well, it's the same thing. It's the two limits being divided, except we do have to make the exception. Well, that denominator can't be 0. But I mean, no surprise here whatsoever. This is good news. Okay, this is a real good news situation. Okay, so now let's take a look at some algebraic fractions. What happens? So the first thing you do with the limit as x approaches 1 is you try to substitute in 1 for x. And what happens when you do that in this problem? I mean, if you plug in a 1 on top, you get 1 plus 1 plus, you get 1 squared is 1, added to 1 is 2. So on the top, you get 4. And on the bottom, you get 2. And you can calculate the limit as 2. No surprise. You notice on the bottom, though, we run into a problem. Here you can't substitute. So we try x equals 1, but we get a 0 on the denominator, so that fails. Now, I don't know how many of you remember, but there is a way to factor the difference of two cubes. X cubed minus 1. There is a way to factor the difference of two cubes. So, I mean, we're stuck right now. We can't do a thing. But what we can do is take that top and factor it. So the first factor is a binomial, and then you have a trinomial. On the bottom, okay, we can't do anything with that. But on the top, so you take the cube root of the first term, the cube root of x cubed is x, the cube root of 1 is 1, and then in parentheses, we get the first term, the cube root of that squared, and on the last term, it's this negative 1 squared. And then in the middle term, it's the product of those two, x and 1. So that would be 1. And it's the opposite sign of that. So it's 1 times x, which is that. So now that we have it factored, we can wipe that out. And now we can substitute the 1 in, and we actually do get a limit here. And any time along the way, we can also do a check. So for example, let's take this expression and let's take a look in Desmos here. So it was x cubed minus 1. You gotta put parentheses around there. Divided by x minus 1. And then as x approaches 1, what happens? Well, 1 would be right in here, and x approaches 1 is right there. Okay? So when you plug in a 1, of course, you're going to get the 0 in the denominator, and that's why it says 1, comma, undefined. So there's actually a hole in the graph right there, but still, there's a limit. It's okay to have a hole as long as from the left and from the right, it's still approaching the same thing. So it's approaching this 3, even though it never gets there. So the limit of this really is 3, and you can see it on the graph. And on Desmos, if you click right on the point, you will see there's a little bit of a hole there. That's okay. That's still legitimate for a limit. Okay. So let's now go to the next. I have another example for you. So how about this limit? What's the limit of this thing as x approaches -3? Well, we can't substitute because that would give us a 0 in the denominator. Is there anything we can do with this algebraically? Yeah, that's the limit as x approaches -3. And on top we have what? X plus 3, x minus 2. And here again, we can do a cancellation, and now we can substitute -3 in. And we can see that the limit of that thing as x approaches -3 is -5. So you see how factoring becomes plays a big role in simplifying limits. Then here's another big problem. What are we going to do with this expression? The limit as x approaches 0 of the square root of x plus 1 minus 1, all over x. Well, you can see substitution does not work because of the bottom. That would create a 0 in the denominator. So we're kind of stuck. We can't factor that. So what's clever is that you remember, I mean, here, let me just go off to the side and remind you of something. So when you remember how this turns out to be special in algebra? That turns out to be the difference of two squares, right? Why? Because if I multiplied that out using FOIL, I would have a squared plus ab minus ab minus b squared. And that plus ab minus ab that's in the middle, they wipe each other out. And so you get this special product. Okay, so we have a name when one factor is the same as the other, but it has the opposite sign. It has a minus sign instead of a plus. That's called a conjugate. So this idea of using a conjugate to get the difference of two squares is what we need to use here. So let me go back now. So can we multiply this fraction top and bottom by something that I can get that x out from under the square root sign on the top? And the answer is yes, we can multiply by its conjugate. So the conjugate of square root of x plus 1 minus 1 is the square root of x plus 1 plus 1. You can't just willy-nilly multiply the top by something unless, you know, it's totally legal because I'm multiplying top and bottom by that, which means I'm multiplying the fraction by 1. Okay, so now what happens? Well, we get the same. You still need the limit notation here. And on top, what happens when you square the square root of x plus 1? The square root sign goes away and you get x plus 1. And then you get the difference of two squares. So the second square, 1 squared, is 1. So that's how the top turns out. The bottom is ugly, but that's okay. We just leave it the way it is. So on the top, I'm making marks here for my hand. Get rid of that. So on the top, what's happened is, what's x? Let's just copy the notation. X approaches 0. On top, we just have x. On the bottom, we have x times square root of x plus 1 plus 1. And we can get rid of that. That's important because if that x was there, we'd have to plug in a 0, and that would make the denominator 0, and we'd be up the creek again. When you divide, of course, we wind up with a 1 on top. Now, can you substitute 0 in for x? Answer, yes. Because on the bottom, 0 plus 1 is 1, and the square root of 1 is 1. So on the bottom, you just get a 2. Right? Square root of 1 is 1, and 1 plus 1 is 2. There's the limit. Let's just take a look at this. We'll just take a look at this in Desmos just to double check. So we've got, I got to get this down, square root of x plus 1 minus 1 over x. Okay, so in Desmos, we have parentheses square root of x plus 1, and it's minus 1, and that's divided by x. Okay, so I forgot. What was our limit? Our limit was as x approaches 0. Okay, so as x is approaching 0, what's going on? Well, that would be right here. Again, it's an open dot, meaning, hey, if you plug in a 0, you're not going to get an answer. But still, do you see where the limit is? It's right at 1/2, right? Because this line here is 1. This is right at 1/2. So we calculated the limit correctly. The graph is heading at 1/2, both from the left and from the right. Therefore, that's a valid limit. Okay. Anybody have any questions about this page? All right. Let's go to the next. Yeah, now we aren't going to need this real much. Well, yeah, we got to watch for this. This is called the squeeze theorem. And the squeeze theorem goes like this. Let's see, I'm going to look at the picture. Okay, so if we look real closely at the picture here, we have 3 functions that are graphed. We have function g in red, function h is graphed in blue, and you notice how function f is graphed in black. All right, what's unique is we can see that function g is headed at the height of, at this point right here, and function h is headed there too, and function f is forever between functions h and g. And so do you see how it goes? It literally gets squeezed, so it's got to agree. So if there's a function sometime that you cannot take the limit of, and those 2 techniques I just gave you don't work, if you can squeeze it between 2 other functions, you can still find its limit. That's the idea behind the squeeze theorem. Okay, and so, like, again, if you know the limit of function g and you know the function of h, and if f is squeezed between it, then we actually can figure out the limit of f. It's got to be c. It's got to be the same at point c. Okay, so the squeeze theorem may play a role. Now, 3 special limits that you must know these. So you've got to write these down in your notes. These are just limits you're going to have to memorize. The first one is the limit as x approaches 0 of the sine of x over x is 1. Now, as you can tell, you cannot substitute 0 to calculate that. I mean, I can show you on a graph why it's true, but there's no algebraic technique we can use. So here, let's go over here. Sine of x divided by x. Okay, so here's what the function looks like. And as x approaches 0, can't nail it exactly. Yeah, it's undefined. Again, you can't plug in a 0, as you can just look over to the left there. I mean, if you plug in a 0, you got a 0 in the denominator. It can't be done. And yet, you see how both the left and right-hand limits of that green curve come right at 1. Okay, so you don't have to do the graphics. I just thought that would help. So anyway, there's a limit you need to learn. The limit as x approaches 0, the sine of an angle divided by that same angle is equal to 1. And then there's two others. When you take the limit as x approaches 0 of 1 minus cosine over that same angle x, that's always going to be 0. And again, you can't do it algebraically. Doesn't work. You can't factor it, you're stuck. So you got to learn this one. And then number 3, this should look familiar from our E day that we spent time on. This is that formula for E, kind of. So if you take the limit as x approaches 0 of 1 plus x, and you take it to the 1 over x power, that's going to approach that special number E. So you want to write those down, okay? Those are very, very important. You're going to need those, and you're going to have to memorize those. There's not a lot you're going to have to memorize, but those you're going to have to know. Okay, so now we get to some limits involving trigonometry. So, and we're going to use those special limits to help us with this. Okay, so this is a limit involving trigonometry. So here it is up on the top. It's this function, the limit as x approaches 0 of the tangent of x over x. You cannot substitute. You can't factor. So what are we going to do? You can't substitute because we'd have 0 in the denominator. So, all right. Now, there is no special limit for this. I mean, if we go back here, there's nothing of those 3 we just learned. There is no tangent up there. Okay. So what can we do? Well, we could rewrite it. So if we're in this line right here, there's the original. Can you see that this is the same thing? So this goes with the, hopefully you remember the ratio identities, that tangent is sine over cosine. So this rewriting of the sine of x over x times 1 over the cosine of x turns out to be exactly the same as what we had in the beginning. Hopefully you can see that. Sine over cosine, so this is equivalent to the thing on the left. Now do you see the function? At least one of them that we had last time as a special. There it is right there on the left. Sine x, the limit of this x, as x approaches 0, this limit of sine x over x, that limit's 1. So this first fraction right here, that's 1. That's what they're telling you, right? That's what they're saying right here. Okay? So that's what we just saw. And can you calculate this one? Yeah, that one, you can do the substitution. If x is 0, what's the cosine of 0? Oh, that's 1. And 1 over 1 is 1. So if you put those pieces together, the limit of that whole thing is 1 times 1. So now we know the answer. The limit is 1. So once again, if you looked at a graph, I guess let's just do it. So we've got tangent x over 1. So let's put that down here. So we've got tangent x over x. All right, and the limit as x approaches 0. There it is. It's undefined. You can't substitute in a 0, but you can see both the left and the right hand. Yep, they're both coming at 1. So that's a legitimate limit. All right. So on this one, you really had to do some work, and you had to know some trigonometry. You had to know that the tangent is equal to the sine over the cosine. And then if you were a little bit clever about how you wrote that, you could get it into a position. So one of them was this guy, was this guy right here. And so, and then we could figure out the other one, because it's okay to have cosine of x on the bottom, because the cosine of, it's okay to substitute. The cosine of 0 really is 1. Okay, so we got it. So that one becomes a little tricky. You got to know a little trig, and you got to know, you got to be able to manipulate fractions. Okay. So let's take a look at this one. Again, a little bit tricky. The sine of 4x over x. Well, that's not, I mean, the only one we know is the sine of x over x. So that's not that famous, that one I told you to memorize. And you can't substitute in a 0. So what in the world do I do? Well, this is going to sound really counterintuitive, but you can actually multiply by 4 and divide by 4. Here's where they multiplied by 4, and here's where they divided by 4. Okay, I'm going to get rid of those because they kind of look crowded. But do you see how they actually multiplied by 4 and divided by 4? You're thinking, why did they do that? Well, now, what's this? If you take the sine of an angle divided by that same angle, that is what this guy up here that I had you memorize. That is that, I mean, the sine of an angle divided by the angle, oh, the limit as x approaches 0, that really is 1. So the limit of the part I circled right here, that really is 1. And you still got this 4, so what's 4 times 1? 4. We have our limit completed. So here again, we got to play what? A little algebraic playing around here. Multiply by 4, divide by 4, got my angle so that the angle on the top and the thing on the bottom were identical. And then we could use that memorized one. So it's a little bit tricky. And again, let's check that out. Sine of 4x divided by x. Sine 4x divided by x. And as x approaches 0, you can just see it. Yep, it's undefined, but you see how both the left and the right are both approaching that 4, so it's a legitimate limit. All right. So let me just review a little bit what we went through here. So first we learned, I mean, there were these basic guys, and you're going to see those in the assignment somehow, where when x approaches c, what's the limit of some other number? Well, x doesn't even affect it, okay? What happens here? The limit as x approaches c, you can just substitute. Plug in a c for x. And here, what's the limit as x to the n? As x approaches c, you can substitute c to the n. So these are pretty basic. Those were not very hard to remember. And then we had these wonderful limit properties that work just the way you'd expect them to. And then we got to some examples. Here on top, you can just do direct substitution. Those are wonderful when those happen. Just go ahead and plug in and do the arithmetic. Then we ran into problems with this one on the bottom, where if you substitute 1, it doesn't work. It gives you a 0 in the bottom. But then we remembered factoring technique. Yeah, how do you factor the difference of 2 cubes? And that allowed us to get rid of that 0 in the bottom. And now we could substitute 1 for x, and you can get your result. This one, we couldn't substitute again. But we were able to factor the top, which allowed the x plus 3 to be canceled, and then you could substitute. And then finally, this troubling one, we use the conjugate technique to multiply, because we know that when you multiply conjugates, you get the difference of 2 squares. And when you square something like the square root of x plus 1, the square root goes away. And then you can, it turns out in this case that x that caused all the problem in the bottom was able to be canceled. And finally, you could substitute, hopefully. And then we talked briefly about the squeeze theorem on this page, although we didn't really see it in action yet. But we know that if a function's stuck between 2 others and we can figure out the limit of the other 2, then we can figure out the one that's being squeezed. And then we went through these examples using trigonometry, and we were looking for these 3 that I had you memorize here. These 3 guys, you need to know those. And we couldn't find it, but we could, because we knew that the tangent was the sine over the cosine. We were able to rewrite a little bit, and then we were able to wiggle our way through. Because, yeah. So, and then this last one, another little algebraic manipulation, multiply by 4 and divide by 4, and that allowed us to get to one of those 3 memorized ones. So, that leads us to the core exercises for 2.3, and here they are. And you've got them on your website, so does anyone have any questions? By the way, I just wanted to add this little note. You said, I don't know, I looked up the temperature in Milwaukee is 7 degrees. Just so you know, where I am, it's 0. But nice sunshine, and on we go. Anybody questions you would like to ask? All right. Thank you. Video should be up in just a few minutes. I appreciate your attendance. Thank you.